Welcome to the second part of Lecture 3. We're going to start our sequence on optimization numerics. We're going to focus on some introductory elements of numerical algorithms today, and then we're going to move on to other aspects of numerical methods, including error and other topics. In this video, we're going to go through a brief review of what we've already covered regarding preliminary numerics topics. We're going to talk about iterative numerical algorithms, algorithm convergence, and termination conditions, and then finally talk about algorithm convergence rates. These are the things that we've already covered. We talked about some of these numerical issues that really are central to engineering design optimization, including the accuracy of our approximate solution, the issues surrounding digital representation, including things like floating point numbers on a digital computer, algorithm stability. Floating point numbers, we did go into this into a little bit depth. One of the main points is that there are holes, these big gaps in the real number line due to only being able to represent a finite number of numbers using a digital computer. So there's an infinite number of continuous numbers that we cannot represent using floating point representation. And because of things like the difference in size of these gaps on the real number line and round-off error, we're going to run into a number of different issues. We went through an example where we saw how having a design optimization problem where the optimization variables differed by orders of magnitude had a big impact on numerical results. It focused on an electric motor design optimization problem, and because of these vastly different orders of magnitude, we really did not converge to solutions that were anywhere close to the correct solutions. And then we went through and rescaled the problem and saw that with appropriately scaled design variables, we obtained accurate multi-objective optimization results. Now let's talk about iterative numerical algorithms. Many optimization solution algorithms take a particular form using this sort of recursion formula, where we are trying to find this value of x being a vector that minimizes a function. And k represents the index or the iteration number of this iterative numerical algorithm. K might start at 0 or 1, and every time we go through and calculate this formula, we are updating the value of x for the next iteration. And then for the next iteration, this value of x becomes the new value here of xk. These iterative algorithms traverse a vector-valued optimization variable space. Suppose we have the case of two variables. The length of the vector x is 2. Here we're going to visualize what one step in this iteration might look like in this space where we have x1 and x2. Suppose here's a point, an arbitrary value of x within the optimization space. We can think of that as a vector, xk. So this is the kth value of x, and we have this vector pointing from the origin to this point. And depending on the optimization algorithm that we're using, we're going to calculate sk, usually depending on the value of xk. And sk is also going to be a vector in the same space. It's going to have the same dimension as x. So suppose we calculate sk, and then we add it to xk. Here, if we have a two-dimensional space, S will need to be composed of S1 and S2. And here's what it might look like if we have some other vector sk in this two-dimensional space, and then we add it as we do with vectors, and then we come up with this new point. And this new point we can think of as a vector on its own, and that's going to be xk plus 1. And just using the rules of vector addition, we can see that, well, in fact, this is the recursive formula that we're using as the basis for many of our optimization algorithms. The step vector calculation is one of the primary distinguishing characteristics of different optimization algorithms. The way we calculate this vector, which could have quite largely varying levels of complexity, is what distinguishes many of the different algorithms we're going to be learning about in this class. In any case, we will typically implement this recursive formula using a while loop. This step vector normally depends on xk. We will be focusing on gradient-based methods. And with these methods, the value of the step vector depends on the gradient of the objective function at xk. Or, in other words, this step calculation, it does depend on xk, but it depends on it in a way where we are going to have to calculate the gradient of f of x as an intermediate step. Sometimes calculating this step vector could require some additional iterative numerical solution at each algorithm iteration. So in other words, suppose k equals 1. So x1 plus s1, which is a function of x1, and that addition will give us x2. But here, if we are starting with x1 and we want to calculate s1, maybe there's a whole iterative numerical procedure that needs to be undertaken to calculate what s1 is. And this is then going to result in nested while loops. So that means for the outer loop, every pass that we go through the outer while loop, we're going to have to execute an inner while loop, and that inner while loop is going to have to complete before we can go on to the next iteration of the outer while loop. There are a couple of examples of this that we're going to see in this class. One involves gradient-based methods, where we're going to usually find the gradient of the objective function, or the constraint functions if it's a constrained problem, and that value of the gradient is going to inform the direction we want to search in. And if we search in that direction, we're going to have to do some iterative exploring and try to find in that direction what's the best point to stop at so that we can make rapid progress toward the overall solution that we're trying to find. And so this is called line search when we're searching in the selected direction, and that's an iterative process, and often we don't know ahead of time how many different samples we're going to need to take during this line search process. So that is an inner loop, while loop, that will need to be implemented in some of your algorithms. Another example involves the algorithm SQP, or sequential quadratic programming. And this is one of the last algorithms that we're going to learn. It's a fairly sophisticated algorithm for solving constrained optimization problems using gradient-based methods. And it involves at each outer iteration the solution of another optimization problem called a quadratic program. A quadratic program is a nonlinear program that has a quadratic objective function and linear constraints, so no nonlinear constraints. And it's a special quadratic program such that if we solve it, it gives us a search direction for us to search along. So actually we have two additional things going on with SQP typically. We have to solve this quadratic program, which is an iterative numerical solution, and then right after that we have to go through and perform a line search typically. And so we have two inner while loops within the outer while loop for SQP. Another method that you have a little bit of experience with now is called pattern search. This is a gradient-free method, and the way it works, at each outer loop iteration for the algorithm, we're going to have to do some testing. We're going to do some sampling of different types, and depending on what we learn during that sampling, we may go through some expansion or contraction steps. And the number of these steps is unknown ahead of time, and we're essentially going to have to perform some iterative calculations before we can move on to the next point as we're searching the space for the optimum. Let's have a look at while loops. Here's a basic while loop that could form the basis of an optimization algorithm. And most of the search strategies, the optimization methods that we're going to be working with in this class require what's called a starting point. And so here I'm just specifying the origin. Here's a vector of length 3, and I'm initializing my my logic condition for the while loop. So I'm indicating that if this variable, not opt, is true or equal to 1, then we are not optimal. So we need to keep going. We need to keep searching while our current point is not an optimal point. And so I'm calling this the optimality flag. Here we have the while loop. While this condition is true, so while we are not optimum, keep iterating. Suppose we have some step function, a function that takes our value of x, the value of x at the current iteration, inputs it into some function that calculates what the step vector is, and it outputs s. And then we do this vector addition. We take our current point x, we add the step, and we get a new point x. And suppose we have another function where we check whether we actually have an optimal point. We're going to have a little taste of how this might actually be done a little bit later in this video. And depending on what we find out, if we find out that it is optimal, then not opt is going to be 0 or false, and then we can stop. And this while loop will test not opt, and it's 0, and then it's going to terminate not opt. So that seems all well and good. This seems like a reasonable process for finding an optimum, but we need to think a little bit more deeply about it. Will all optimization algorithms always find an optimum? Are there cases where an optimization algorithm might fail? And if that's the case, if it can fail, then what implications might there be for this while loop? Are there even problems where a finite optimum does not exist? We're going to learn a little bit later about problems that have issues with boundedness. There are problems that we can define that do not have a finite optimum. They are unbounded problems. And there are other different types of formulation issues that we're going to run into and we're going to explore in later lectures. So if an optimum cannot be found, either because it does not exist, or because for some reason the algorithm is incapable of finding it, what happens with the while loop? Are there any issues that we might run into with this while loop, the way that we've defined it? How might we terminate while loops used for optimization algorithms? In this case, the only way this while loop is going to terminate is if our check opt fun function sets this variable not opt to false or 0. But if we never find the optimum, this will never be set to 0, and we will be in an infinite loop. So we need some additional ways of terminating this while loop. Let's have a look at one simple way of making sure that the while loop will always terminate, even if we give it a problem that does not have a finite optimum. This is a simple approach. We can set a maximum limit on the number of while loop iterations required. So here's an expansion of the code that we just had. In addition to initializing the starting point and this not opt flag, I'm also including an index, a counter that tells us what iteration we are on. And then I'm setting a limit on the maximum number of iterations allowed for the while loop. Here we start the while loop. Everything is the same so far. And then in this next line, we increment the iteration counter. Here, well, in Matlab, we don't have the syntax I++ to increment an index, so we have to use this syntax I equals I plus 1. Then we calculate our step vector, we do the vector addition, we check and see if it's optimal or not, but then we add in this one more check. So there are two different ways we can now terminate the while loop. We can either stop because we found an optimum, or we can stop because we have exceeded the maximum allowed number of iterations, and then we break the while loop. How can we set an iteration limit for the built-in Matlab optimization functions? This is something that you can do with the functions that you've started to get some experience using now. You can use the optimSet function to modify some of the fields in the options struct, and one of those fields is the maximum number of iterations allowed, or the variable name is maxiter. And so here I'm setting it to be 100, and that's actually a rather low number for most problems. And you might it might be helpful to go in and learn things like, well, what's the default? If I don't change this, what the maximum number of iterations are, what is the default value of the maximum number of iterations? It does have a default. If you don't specify a maximum limit, the Matlab built-in optimization functions are going to make sure they still have the safeguard in place, and there's some default limit built in. How will I know if a Matlab optimization algorithm terminated due to exceeding the maximum allowed number of iterations? If you have a look at the fmin_con syntax, for example, if we specify that we want to have 3 output arguments, we're going to get the value of the optimal optimization vector. We're going to find out what the objective function value is at the optimal point. And then we get one more piece of information called the exit flag. And this is an integer, and it gives us some information about how fmin_con terminated. And if we terminated because we exceeded the maximum number of iterations, then the exit flag is 0. It's important to keep in mind that this way of terminating a while loop is really just an algorithmic safety net. Usually if we terminate because we've hit the maximum number of iterations, there's something going on, either with the problem formulation that we specified, or maybe there's some other kind of numerical issue that's going on, and it requires some additional analysis, and you're going to need to take some kind of action to solve the problem in a more satisfactory way. Let's have a look at some additional stopping criteria. If stopping due to hitting this limit is not the preferred way of stopping an algorithm, how else might we terminate an optimization algorithm? The ideal outcome is that we converge to an optimal solution. We want to terminate and find the solution, a local minimum that we are looking for. To proceed, we need to dig a little bit into what some of these terms mean. First, let's talk about the idea of algorithm convergence. What does it mean for an algorithm to converge? Think back to when you took your course in Calculus 2 and you went through infinite series and sequences. What does it mean for an infinite series or sequence to converge? For example, what about the Fibonacci sequence? We can define it using this recursive formula where k is the iteration number, or the index for the element in the Fibonacci sequence, and k then is going to start at a small number, and we're going to define ak as the sum of the two previous values. This recursion relationship defines this infinite sequence, sk. Here's a question: does the Fibonacci sequence converge? If k approaches infinity, what happens to ak? A convergent sequence is one where the limits, either approaching an upper or lower limit, approach this same value, and as k gets larger and larger and approaches infinity, then we more precisely, or we get closer and closer to this value s. That's what it means to converge. Here's an example of a converging sequence where n is the index for the sequence, and as we increase n, we are converging to a finite number. Now that we've talked briefly about the convergence of sequences, what about the convergence of algorithms? What are the different ways an optimization algorithm can converge? And notice that this general formula for an optimization algorithm looks a lot like the recursion relationship that we had for sequence definitions. So does this recursion relationship have a finite limit? If it does, then this algorithm is going to converge to a point. Whether or not it has a finite limit depends on two different things. It depends on how we define the algorithm step, or in other words, what is the optimization algorithm that we're using. And it also depends on the problem being solved. As we mentioned a few minutes ago, it's possible that a problem has no finite solution, no finite minimum, and if that's the case, we may have a perfectly good algorithm, but it's not going to converge to an optimal solution because it's an unbounded problem. Something that's important to remember is that if we terminate because we've exceeded the maximum number of iterations, that is not considered algorithm convergence. We've basically been caught by the safety net. Let's talk about optimization variable convergence. The optimization vector approaches a point attractor, or in other words, as we increase the number of iterations, the value of the optimization vector x gets closer and closer to a point, and that is the value that we are converging to, or it could be called a point attractor. Also, another property of convergent algorithms like this is as the algorithm progresses, as the number of iteration increases, the step size decreases. And because the step size is decreasing, that's a property that we can keep an eye on as we are proceeding through an algorithm. The basic idea is to stop the algorithm when the step size is smaller than some tolerance. Or in other words, we are observing that the value of x stops changing within some small tolerance. We have to have a tolerance. We're not going to reach the limit value exactly, because this is an approximate numerical algorithm. And so we're going to have to set some tolerance that specifies quantitatively how close to or how little change are we going to consider to mean that we've stopped changing, that we've actually converged on a point attractor. Here's one way of doing it. We can take a look at 2 points in the sequence, xk and xk plus 1, and we can then look at how far we moved. So here, this indicates I'm taking what's called the Euclidean norm or the L2 norm, or in other words, what is the distance between xk and xk plus 1 in a Euclidean space sense. And we check this distance every time we take a new step, and we compare it against a tolerance. Here I'm calling that epsilon 1. And as soon as this distance is less than or equal to epsilon 1, then we consider that our algorithm or the sequence xk has converged, and we can terminate the algorithm then as long as no other termination conditions have been satisfied previously. Here's a question. If the point the algorithm converged to, or is the point that the algorithm converged to necessarily an optimum? Is there some way it could converge to a point that is not an optimum? We've not really gone through these algorithms in much depth yet, and so I don't really expect you to have a lot of intuition for the answer to this question, but it's important to know that we can converge to points that are not an optimum. So the answer to this question in general is no. We can't guarantee that if x stops changing, or in other words, that alone is not enough to say that we are actually at an optimum, because there are some other points we possibly could converge to. We could converge instead to a maximum, depending on the algorithm we're using, or something called a saddle point, or we could have a sequence x that stops changing due to some other numerical problems that are going on. Another type of convergence is objective function convergence. The optimization function output approaches a point attractor in this case, or in other words, as the algorithm progresses, the output of the function, the amount it changes decreases. Similarly, we can specify a condition where we look at how much the objective function output changes, and we compare that change to another tolerance, here I'm calling that epsilon 2, and if the change is less than or equal to this tolerance, then we terminate. Again, as with the optimization vector convergence due to the objective function output stopping changing, that also does not guarantee that we have found an optimum, but it is a type of algorithm convergence. Let's talk about more general algorithm termination conditions, whether it is convergence or some other type of termination. We can terminate for a number of different reasons. Of course, the maximum number of iterations, or in addition, we can set a limit on the maximum number of function evaluations. And you might wonder what the difference is there. The maximum number of iterations basically refers to how many iterations the outermost while loop has gone through. But each time we go through a single pass of this outer while loop, it might require a large number of function evaluations, meaning evaluation of our objective function or constraint functions. And that might be something we want to constrain as well, especially if there's some possible situation if within a single iteration of the outer while loop we have some kind of numerical algorithm in an inner while loop, and there's potential for that to keep going without bound. And so we want to have that safeguard as well. Another possibility we just went through is that the optimization vector has converged, so that's another termination condition that we check. Also, the objective function output has converged. We just had a look at that. Another reason might be if we are solving a problem with constraints and we're trying to find even a single point that simultaneously satisfies all the constraints, or in other words, we're trying to find a feasible point. What if we can't find one? It is possible to define problems such that no feasible points exist. There's no point that satisfies all the constraints simultaneously, and that's not a very well posed problem. But there's also the possibility that feasible points do exist, but given some starting point, a particular algorithm is unable to find from that starting point a feasible point. Another way that we could stop, and this is the ideal, is if an optimum has been found. But how do we know if we have found an optimum? It depends on the class of problem that we are talking about. Here we're going to go through a quick introduction to optimality conditions, specifically for the class of problems that we are focusing on in this class. Smooth, continuous problems where we have smooth, continuous functions and real, continuous variables that are input to these functions. So what does it mean when an optimum has been found? How do we know when it's been found? We need to apply mathematical optimality conditions, and these involve typically what we call necessary and sufficient conditions. And these refer to whether a point could be an optimum or definitely is an optimum. And we'll talk about the distinction or the nuance there in just a moment. And in this course, as I've mentioned, we're focusing on these problems that have continuous functions that are smooth, differentiable, and real continuous optimization variables. And for this class of problems, the optimality conditions depend on the first and second derivatives of our functions. There are other classes of problems that do have optimality conditions that can be derived, including things like integer programming, at least certain classes of integer programs. And there are even some non-smooth continuous problems where we can actually prove something about optimality based on something called Clark's calculus. This involves something called subgradients. So essentially some non-smooth functions, it is possible to still derive optimality conditions, although that is a fairly special case. Just a note here on local minima. When we are talking about finding an optimum, in this class we are almost exclusively referring to a local optimum. Most practical engineering design optimization problems applied to physical systems are non-convex problems. And as we went through previously in the section on mathematical preliminaries, we learned that when we have a problem that is non-convex, that we don't have a guarantee that if we find a local minimum, it's going to be a global minimum. So in general, these non-convex problems are quite hard to solve. Typically, we cannot guarantee ever that we've found a global minimum. There are some special cases where, yes, we can guarantee a global minimum for nonlinear programs, but that's not in general true. And for the practical engineering design optimization problems that are focused on physical systems, typically we just never can say whether we have a global optimum or not, but we usually can improve the probability of finding a global optimum. We just can't prove it. So in most cases, the best we can claim regarding engineering design optimization is local optimality. And some people might wonder, well, why go through the effort if it's just a local optimum and not the global optimum? Here we're going to assert that finding a local minimum is actually of value in engineering practice. We are going to discuss this point a fair amount in a later lecture, but for right now, just proceed with this assumption that it is valuable to find a local minimum. Let's talk about necessary conditions from the perspective of logic. These are logical conditions. Essentially, if we have something is true, say if A is true, then B must be true. This is what we refer to as a necessary condition. So for A to be true, B must be true. Or in other words, the truth of B is necessary for the truth of A. So if A is true, then B is always true. If B is going to be true, or if we're wanting to find out if B is going to be true, then B is never going to be true if A is not true. So A is necessary, or B is necessary for the truth of A. It's important to observe that B being true does not guarantee the truth of A, or in other words, B is not sufficient to demonstrate the truth of A. Now, this might seem like a tangent, but at least wrapping your mind around the nuance of necessary conditions and sufficient conditions and the combination of necessary and sufficient conditions is a really important aspect of understanding optimality conditions. We often will talk about necessary and sufficient conditions for optimality. Essentially, if we satisfy necessary and sufficient conditions, then that's sort of like when you've encountered proofs in mathematics. If both necessary and sufficient conditions are satisfied, then you can say A if and only if B, just for example. So these sorts of conditions enable us to prove whether a point is an optimum, and also just understanding these optimality conditions or stating these optimality conditions. This is a really common starting point for numerical optimization algorithms. And this is actually how we're going to proceed later in class. We're going to be starting with defining what are the optimality conditions, and then we're going to take multiple paths from these optimality conditions to different algorithms that are useful. Optimality conditions for local minima. Assume that we have first and second derivatives that exist for a function f of x, and let's suppose this is a case where x is a scalar. This is a univariate function f. And suppose we have a point x star that we are saying is a local minimum of the function f. If it is a minimum, then the following equations hold. For x star to be a minimum, this must be true. The derivative of the function with respect to x must be equal to 0. This is a necessary condition. But then it is possible to have a point where the derivative is equal to 0 and have a point that's not a local minimum. And so this condition by itself is not enough, but the combination of this condition on the first derivative along with this condition on the second derivative is enough to say that yes, this is definitely a local minimum. Essentially, this second derivative gives us curvature information, and if the second derivative is positive, then that means this is a function that is concave up. It's going to have a local minimum because of the shape of its curvature. These two equations combined then are necessary and sufficient for x star being a local minimum. Let's talk about the other cases, stationary points and inflection points. A stationary point is a point x dagger that satisfies the following equation. So the main difference is we're going the other direction. Previously, we started with a point we knew was a local minimum. Now we're starting with a point that all we are saying is it satisfies this condition. The derivative at this point is equal to 0. And I'm using a different symbol, x dagger, instead of x star, to make a distinction, to make it very clear that this is a special point, but we don't know if it is a local minimum or not yet. We call x dagger a stationary point. So why do we call it a stationary point? Well, imagine a curve, a function of one variable, and think about any point where this might be true. And the way to think about that is if you have a tangent line at a point x, a line that's tangent to the curve of the function f. Whenever this is true, the slope is 0, the tangent line is going to be horizontal. And if you have, say, a ball that is placed on a surface right at a point where the tangent line is horizontal, then that's a stationary point because the ball's not going to move. It could be a stable or an unstable stationary point. If it is actually at a minimum, then that's a stable stationary point. So if this equation holds, if this is a stationary point and the derivative of f of x at x dagger is equal to 0, x dagger could be a minimum, but other possibilities exist. So if it is a stable stationary point, then yes, it is a local minimum. But what are the other possibilities? It could be a local maximum. And if you imagine the function looking like the top of a hill and you put a ball on the top, well, if it was perfectly balanced, it's going to be stationary. But what if you have some disturbance either direction? Then it's going to roll downhill, and that's not a stable stationary point. Or an inflection point, or sometimes called a saddle point. And we'll get into this in more detail, and it'll make more sense when we get to multivariate cases why this is called a saddle point. But for univariate case, just imagine a function that is increasing, but then its slope is decreasing, and then it goes flat. But instead of going back down, it then starts to increase again. That's what we call an inflection point or a saddle point. So at that point, the derivative may be 0, but it's also an unstable stationary point. If we have a disturbance, it could roll downhill. Second order conditions related to curvature will help us to distinguish between these cases, a local minimum, local maximum, or an inflection point. If a point is a stationary point and the order of the first non-zero higher derivative is n, then the following are sufficient conditions for x dagger to be a local optimum. So it has to be a stationary point to start off with, and then we need to look at these other conditions. If n is odd, then we are looking at an inflection point. If n is even, it could be either a minimum or a maximum. So if the first non-zero higher derivative, we're looking at the nth derivative, is greater than 0, then that means we have curvature facing up, and this is a local minimum. If it's less than 0, we have curvature facing down, and that's a local maximum. Let's have a look at an actual example regarding optimality criteria. Say we have this cubic function, and it's plotted over here. We can see it actually has both a minimum and a maximum. And this is something that's pretty typical of a cubic function. Suppose we want to find a local minimum of this function using optimality conditions. So optimality conditions involve the first order optimality conditions, looking at the derivative being 0, and then also the second order conditions looking at the sign of the second derivative. Here, let's take the first derivative. That's pretty easy using the power law, and then we can very conveniently rearrange this algebraically, and we want to see where does this derivative equal 0, or for what values of x is the derivative 0. And by arranging this result in this way, it's very easy to see what the roots of this equation are. When x equals 2, the derivative equals 0. When x equals minus 1, the derivative equals 0. So these are the two roots, and then at each of those roots, these are the objective function values. So let's have a look at these roots on the plot here. So at x1 equals 2, right there. Oh, well, it's pretty clear that is a local minimum. But then if we have a look at, let's see, so x1 equals 2, that was f of x1. Let's have a look at f of x2. x2 is minus 1. Oh, well, that's a local maximum. And that's great if we can visualize it, and that's fine with inexpensive functions of a single variable. But as we've discussed before, visualization really is a brute force solution approach, and we'd like to find the solution without having to visualize. We want to minimize how many times we evaluate the objective function as we work to find the solution. So let's have a look at the second derivative here, and then we can evaluate the second derivative at both of these stationary points. So these two roots, x1 and x2, those are both stationary points. And to say authoritatively whether one is a minimum or a maximum, we can do that by looking at the second derivative. At x1, we have a case where the second derivative is positive, and that is therefore a local minimum. But at x2, the second derivative is negative, and so therefore it is a local maximum. So that's a simple example in one dimension, but what about n dimensions? How do we extend to n dimensions? In the second part of class, we're going to go through this in a lot of depth, but I'm just going to give a quick preview now of what this entails. Instead of requiring that a tangent line at a stationary point is horizontal, we require that the tangent plane at a stationary point is horizontal, and in this case the point is defined as a vector instead of as a scalar. So we are requiring that every element of the gradient of the objective function is equal to 0. And here in my notation, when I use this bold-faced 0, that means the 0 vector, or the vector that's the same length as the gradient of f of x. So it has the correct number of components. So if x is of length n, then the gradient of f of x is length n, and then the length of this 0 vector is length n. We can derive what the gradient of f of x is if we have, say, algebraic expressions for f of x. And if we have that, we can think of this as a system of nonlinear equations. We're going to have some result. If we derive what the gradient of f of x is, we're going to have some symbolic result for each one of the components of the gradient, and then we set that equal to 0, and so we have this system of nonlinear equations. So how many equations and how many unknowns? Well, the number of equations, that's going to be the number of rows in the gradient, or the length of the gradient, and the number of unknowns is x, or the length of x. We don't know what x is. Each one of the components of x is an unknown. So we have n equations and n unknowns if n is the length of x. How might this be solved? Well, we have this nonlinear system of equations, And we could use some general numerical solution algorithm for solving nonlinear systems of equations. And this might be something you've seen before. You've certainly solved linear systems of equations, but many nonlinear systems of equations are not solvable just by hand. Often you need to use some sort of numerical method to solve those equations. So we could do that. We could solve we can solve the system of equations, but we could run into some problems. Remember, in the univariate case, if we were to find a stationary point, it could be a minimum, but it might also be a maximum or a saddle point. So that could be a problem. If we are solving the system of equations, really all that's doing is finding a stationary point. And we're going to have to dig a little deeper if we want to determine whether that stationary point is in fact a minimum. So why are points like this called stationary points? In this case, where we are extending to multiple dimensions, maybe think in terms of a function of two variables. And so f of x then is going to be some nonlinear but continuous and smooth surface as a function of x1 and x2. So it's going to be varying around, and we want to find the minimum. Again, it's like we're trying to find the lowest point in a valley. And if you imagine a ball that's placed at some starting point, and if it's a smooth surface, we let the ball roll down, it's going to go downhill and eventually settle in a local minimum. But what if we very carefully place that point on the top of a maximum? Then that's a stationary point. It's an unstable stationary point, but it's a stationary point because the ball's not going to move. And then this also could be true for saddle points. Let's talk about termination conditions specifically in Matlab. So this is going to be helpful when you are using the built-in Matlab functions and understanding how to specify things related to these different termination conditions, such as the tolerances that are associated with them. If you don't provide your own updated options struct to methods or functions like fmincon or fminunc, then Matlab will specify default tolerance values. And if you want to see what those are, you can go to the Matlab documentation, especially go to OptimSet, for example, and see what the different available fields are for the different functions like fmincon and fminunc. We can specify tolerances for a wide number of things. Of course, the maximum number of iterations and function evaluations. We can specify tolerances on optimization variable convergence. So what is the epsilon value that we're using to decide when x has stopped changing? And we can do the same thing for function convergence. We also have a tolerance for optimality condition tolerance. We've not looked at that yet. We're going to look at it in just a little bit more detail in a moment. Constraint satisfaction tolerance. This is something else that's important. It is distinct from, say, looking at convergence, but when we are trying to find a feasible optimum, we need to be able to say quantitatively that we have satisfied our constraints. And this tolerance helps us to know with what accuracy we are solving or satisfying these constraints. Let's have a look at these different things that we can change regarding the tolerances and settings for termination conditions in Matlab. So max iter, the maximum allowed iterations. We looked at this previously. We use OptimSet to change the max iter field, and here I changed it to 100. And just as a reminder, so you know how this is being used, if we only change this one field, then OptimSet is going to produce a struct, and here I called it my options. You can name it anything you want. And everything is going to have the default value in it, except for the max iter field, and that will be 100 instead of whatever the default value is. And that's something that you should have a look at. You should become familiar with what some of the key default values are for the algorithms that you're learning to use. If we've created this new option struct, then that is passed in here as the last input argument, at least with this version of the fmincon implementation. Tall_x, that allows us to specify the optimization variable convergence tolerance, and it uses this same format. We can change what the tall_x value is in the option struct, and just as a reminder, it corresponds to this value of epsilon1 that we looked at a few minutes ago. And if you're wondering, well, what is this Euclidean norm, or what is this norm that I've denoted right here? If it's not specified what it is, these double lines usually indicate what we call the Euclidean norm, or the Euclidean distance between 2 points, or it's sometimes called the L2 norm. And if this is something you're not familiar with, you definitely should look it up. Make sure you're familiar with what the Euclidean norm is. Suppose we have a vector. Here's a vector x. I just defined it using the Fibonacci sequence. And we could use this function in Matlab called norm. And if we don't specify any unique settings, it defaults to the Euclidean norm. And so if I were to evaluate the norm of x, then I could store that value here that I've called the magnitude of x. Let's have a look at tall_fun. This is the function convergence tolerance. We can specify that in the same way we've specified all the other tolerances. And this corresponds to epsilon2 that we looked at before, or the smallest value we are allowing the objective function to change before we consider it to have converged. Let's talk for a moment about numerical satisfaction of equality constraints or equality relationships. We have several different types of equality constraints that we need to satisfy. For example, we may be looking for stationary points. We want to find points such that this set of constraints is satisfied. And similarly, if we have equality constraints in our problem, we want to make sure that these are satisfied as well. Let's think about equality constraints, though, in the context of a digital computer using floating point numbers. Equality constraints can be checked exactly for some numbers, such as integers or other numbers that can be represented exactly in the floating point number system. But what about more general real numbers in floating point representation? In numerical algorithms, because of these precision limits, we can only satisfy equality constraints approximately. We need to specify a tolerance so that we can decide whether we have satisfied these equality constraints well enough to consider them satisfied. So think back to this fence analogy that we looked at before. Say if we want to find the minimum of a valley, but if we have an equality constraint, that means we have to stay on the fence. And mathematically, this is just a line, a curve. It has no thickness. But if we allow a tolerance, then that means we are essentially tracing out a parallel line on either side of the fence. And so you can think of this as a thick fence, or the fence has width. And so as long as a point that we are considering is within the boundaries of this thick fence, then we consider that the equality constraint has been satisfied. So how can we quantify this accuracy? Suppose we have a nonlinear, or actually this is a linear constraint. We want x to be equal to pi over 2. And pi over 2, this is an irrational number, so that's probably something we're not going to represent with perfect precision in a floating point number system. We are essentially saying we need to stay within a certain distance of the fence. And the fence is where the equality constraint is satisfied exactly. And if we specify a tolerance here, epsilon 4, then if we have a value x, we want to make sure that it is within a distance, epsilon 4, of pi over 2. We can also represent that here using the absolute value sign instead. And then we can also look at a multivariate case. And I should point out this really is a simplification. Here we've essentially lumped everything together using a norm, but really we could be treating each one of the elements of the output of h of x separately using a different tolerance. But algorithms will typically have a single tolerance that's applied across equality constraints. And this gets to part of the importance of scaling our problems properly. So it's not just the design or optimization variables we need to scale. We also need to make sure that the outputs of our functions are also similar orders of magnitude so that these tolerances can be applied consistently and get essentially the same level of accuracy for all of the functions. Tolfun. This helps us to specify optimality condition tolerance. Remember, optimality conditions, at least the first order optimality conditions, are necessary conditions. We set the gradient equal to 0. And one way of expressing the tolerance here is that the norm of this is less than or equal to some tolerance. Now, notice we've seen Tolfun before. We've already used Tolfun, and so that's why I'm saying epsilon 3 is equal to epsilon 2. At least in Matlab, the specific tolerances that we have control over, Tolfun, it is used in two different ways. And so the second way that we're seeing it being used here is for optimality conditions and not just for convergence of the objective function. We can specify Tolfun as with all the others using optimset. Here we have a separate field, Tolcon, for constraint satisfaction tolerance. Here are the constraints we want to satisfy, and here's at least one way of quantifying how well we have satisfied these equality constraints. The size of this tolerance is going to dictate the thickness of the fence in the analogy that we were looking at before, and we can use optimset again to set that value to something that's besides the default. So now we've talked about a lot of the things that you can adjust before we run fmin_con or fmin_unc. But what about after we run the optimization solver? How can we tell how the solver terminated? We're going to look at how we can see what termination conditions were exercised. And we've already talked some about this. If we specify a third output argument for fmin_con, exit flag, this is the output that tells us how the algorithm terminated. It's really important to look at this exit flag. This is something that's really easily overlooked, and one of the really common issues I will see students running into if say there's a numerical optimization solution and it just doesn't make sense. What if we look at the exit flag and we find out, oh, well, it's probably not actually a local minimum based on the exit flag. So there are a bunch of different possibilities, and typically if the number is positive, so the exit flag is going to be an integer, And if that integer is positive, that's one of the better outcomes. If it is negative, that's not a good outcome. So the ideal flag we want to see is 1. This means we have found a feasible solution that satisfies optimality conditions. Or in other words, yes, we have found a local optimum. That's what you want to see. 0, that's when we hit the maximum number of iterations. You don't want to see that. If you see that, you need to figure out why that happened, what has been overlooked. -1 stopped by the output or plot function. fmin_con or other optimization functions have this option of allowing you to specify a plot function that allows you to visualize the progress of the algorithm as it's going. And that can be really useful, but if you define your plot function that's helping you with this visualization such that it could have an error depending on what you're visualizing, then that could cause algorithm termination as well. And so that's what this -1 refers to. -2, that's not a nice thing to see. This is where maybe your starting point was not feasible and you plug it in, and sometimes fmin_con can search and successfully find a feasible point, even if your starting point is infeasible. But if it can't, then it'll stop, and this is what the exit flag is going to be. Exit flags 2 and 3, these are the cases where we've actually converged, and that's a pretty reasonable result, but we're not sure whether it's an optimum. And so there are things that we can do to check the nature of the result here. We can essentially just have a look at the optimality conditions. It might be the case that either x or f of x stopped changing. Maybe we really are converging on a minimum, but we did not satisfy optimality conditions. We did not get close enough to the gradient being equal to 0 before x or f of x essentially stopped changing. And so if that's the case, then you need to have a look at the optimality conditions. We'll learn more later about how to actually do that with fmin_con. And if it looks like we're close to being optimal, then maybe something like scaling or something else needs to be done so that we can actually find the optimum before x or f of x stops changing. There are a number of other things to watch out for. Looking for unbounded solutions. We'll talk a little bit more about this next week. If we have an unbounded problem, we'll usually, that's one of the things that will cause us to hit the maximum number of iterations. Another thing to look out for is if any of the objective or constraint functions encountered not a number. And if you're not familiar with an NaN output for Matlab, I recommend that you have a look at the documentation for that. Also, you should be checking the feasibility and optimality quantities in detail when you have a solution from one of the Matlab optimization functions. This is part of what we call solution analysis, and this is an important part of the overall problem formulation cycle. We need to understand the nature of the solution. Is it a good solution? Is it telling us something more? Is it giving us insight into how we might reformulate the problem in a more useful way? And if we do this analysis, it could provide a lot of information. And another way of thinking about it is, if we have made a mistake in how we have formulated the optimization problem, then often trying to solve that problem using a numerical optimization algorithm will reveal that something is wrong. We're going to have an undesirable exit flag, or something just doesn't make sense. And we're going to learn in a lot of detail what to inspect about solutions to make sure that it's something that we can be confident in, or we're going to look at what a lot of the red flags are that you need to pay attention to, that are things that are indicating that you need to improve something about the formulation. Okay, next topic. Let's talk about algorithm convergence rates. We've talked about what it means to converge, but what about the speed with which an algorithm is converging? We're going to talk about desirable algorithmic convergence properties. We'd like to have algorithms that converge quickly. We want to get to the precise solution with very few function evaluations. We like algorithms that have stable behavior. There are cases where we could have unstable behavior. We're going to go through some examples of that case where either we have an algorithm that just keeps oscillating, it keeps jumping around to different points or different regions of the optimization vector space, or maybe it diverges. It just goes off to increasing values, and it does not go to a point attractor instead. We want an algorithm that has a descent property. We want it to make progress toward a minimum. So these are all desirable convergence properties. We're going to focus a little bit here on convergence rates, where we have ways of quantifying how fast an algorithm is based on its corresponding sequence. Also, there are a couple of terms to define here: local convergence and global convergence. When I say local convergence, if an algorithm has good local convergence, that means if we provide a starting point that's at least somewhat near an optimum, the algorithm can converge really quickly to a precise value of the optimum. It can find the solution fast. There are a number of algorithms that have this really nice local convergence property, but those algorithms sometimes have some other problems, including with this issue of global convergence. This means that if we start at a starting point that is maybe farther away, not really close to a local optimum, if we have an algorithm that has good global convergence, then we are going to more reliably get to the local optimum. And this often corresponds to algorithms that have this descent property. If we're far away, but we have a descent property, then that means we're going to keep going downhill, and we're going to more reliably find a minimum. I need to be clear here, when I'm talking about local and global convergence, this is a completely distinct thing from when in the past we've talked about local and global optima. So local optima, these are things that can exist in a multimodal problem or non-convex problems, and a global minimum, that is the smallest value objective function that satisfies all of the constraints. So that is very different from what I'm talking about right here. Local convergence, that means if you're close to a solution, you can get to the solution really fast. Global convergence means you do a good job of reliably getting to the solution. So let's have a quick example to talk about the difference between good global and local convergence. Here's a sketch that I made up with the level sets in a two-dimensional space. We have two optimization variables, x1 and x2. We have a local min right here with a value of 0, and we have a local max up here with a value of 100. And both of these are stationary points. And with this, I can talk a little bit more about what I mean regarding local and global convergence. So suppose I'm starting over here. I'm starting at a point that's pretty close to our minimum. And if I have an algorithm that has good local convergence, it's going to go really fast to this minimum, and it's not going to take many function evaluations to get there. There are algorithms that have other good properties, but maybe they don't have good local convergence, and an algorithm with poor local convergence is going to be one that's going to take many, many steps, many function evaluations to get to a precise solution. Or when I talk about a precise solution, think about the number of significant figures, for example, or the tolerance with which we are satisfying optimality conditions. We want to get a really precise solution. So that's a discussion of local convergence, not local optimality. Let's talk about global convergence. Suppose I have I'm starting at a point up here. And if I have an algorithm with a descent property, here I'm on the side of a hill. If I were to go up, that's going uphill. If we have a descent property, it's going to keep us going downhill. So if I have an algorithm that can reliably get us down to this minimum from many different starting points, maybe I'm starting clear over here, and it finds a path down to the minimum. That's good global convergence. What about poor global convergence? It turns out there are algorithms where, say if I start right here, instead of going toward the minimum, it's going to find the nearest stationary point. It's going to really rapidly converge on the local maximum. And we don't want that to happen. So it's ideal to have an overall algorithm that has both good global convergence to avoid this kind of situation, and good local convergence. Once we get close to the minimum, it can just really rapidly find the precise solution. Okay, let's talk about convergence rates. Linear convergence. Here we are thinking in terms of the sequence generated by the algorithm. This set of points in sequence, x1, x2, x3, where k goes from 1 until the end of the algorithm, and we're interested in how rapidly we are making progress. And this formula quantifies how quickly we're making progress. So x star, that's the solution. And we see that on both sides here. So what does the left-hand side mean? Well, this is the distance our updated point is from the solution. And then here on the right-hand side, that's the distance that the old point is from the solution. And then what's gamma? Gamma here is a scalar that's between 0 and 1. And so if gamma is less than 1, then we're saying that this distance needs to be smaller than this distance over here. And if we can find a value of gamma such that this inequality constraint is satisfied for all of the values xk in the sequence, then we can say that we have an algorithm with linear convergence. We can test this empirically. Say if we use an optimization algorithm and we store in memory all of the points that are visited along the way at each of the major algorithm iterations, so the outer while loop, then if we have that sequence, we could go through and test these distances, and we could try different values of gamma until we find a value for gamma such that this is satisfied. Now, linear convergence is actually the slowest class of convergence. So this set of inequality constraints is not as difficult to satisfy. And so we're interested in some more stringent requirements as well. So what are some faster types of convergence, or sequences that are just fundamentally converging faster than linear convergence? Here, this is what we call superlinear convergence. The formula looks very similar to the previous one, but the difference here is instead of choosing a value of gamma that does not change, here we need to define a decreasing sequence of gamma. And so this means that not only is this expression on the left-hand side always smaller than the one on the right-hand side, the ratio by which it is smaller is getting stricter and stricter as the sequence proceeds. So this is what we call superlinear convergence. And if we were to try to empirically identify whether an algorithm has superlinear convergence, we would need this sequence, xk, and we would need to test different decreasing sequences for gamma k. And there are different ways of defining decreasing sequences. You can go back to your Calculus 2 book and look at some examples. But it is possible to show for classes of algorithms that actually do exhibit superlinear convergence for us to show this empirically. If you were to take a more mathematical course in optimization, a more proof-based course, you could do this not just empirically, but you could actually prove that different algorithms have certain convergence rates. Quadratic convergence is the fastest convergence. It looks almost the same as the linear convergence formula. Here we have, again, a value of gamma that's not changing, but the key is the right-hand squared. We're taking the square of this L2 norm. Here we have all of them compared, and I think it's useful to have a look and make sure that you understand the differences between the two. And so I like to have these all on the same page as I'm thinking about the differences between the different classes of convergence. And it's especially helpful, I think, as we get farther into this class, as we explore different algorithms that have linear, superlinear, or quadratic convergence, to actually pay attention, to have a look at the sequence of points generated using the different algorithms we're going to learn about, and pay attention to the rate at which the sequences converge. Okay, that's the end of this part of Lecture 3. I hope it was helpful, and I'll see you next time.